Okay guys, notes for today on graphing rational functions. Our big learning target for this section is going to be to understand what the components of functions create visual features. So what I mean by that, in layman's terms, would be that what components or what pieces of the equation make these visual features, so things that look different or that are special about rational functions. So what equation part makes it look a certain way? Whoop, kind of got stretched down the side there. Okay, so let's look at some features here. So we've got a couple. This right here, these dashed lines, these are indicative of what is referred to as a vertical asymptote. It's a cool word, right? Vertical asymptotes. So vertical asymptotes are caused by that division by 0 or trying to divide by 0. And then we have some here. Let's do this one in pink. This right here, pink piece, this is called a horizontal asymptote. And we'll look at what causes that. And then this guy right here, this open circle, is called a hole. And they're kind of weird. We haven't looked at those very much yet, but we'll be looking at those as we progress through this. So we've got our vertical asymptote, we have our horizontal asymptote, we have our purple little there, that's a hole. Some of them have x-intercepts, a lot of them don't. And then we have right here, that right there is our y-intercept. You notice I've got all my handy dandy colors out to help me really be clear about what exactly I'm talking about as I coordinate my notes. It's a great strategy. Okay. The key features in rational functions, most of them, are created as we encounter issues with the domain. Okay. For rational functions, that generally means here, that means trying to or approaching division by 0. Division by 0. So domain issues and division by 0. It's almost like I'm annotating my own notes as I go through there, you guys. So some notation that we've talked about in the past. Mine got hole punched, sorry. So when we're talking about end behavior, the notation that generally goes with end behavior is something like this. We've done this in the past. As x gets infinitely large, as x approaches infinity, you might see f of x or you might see y. Y approaches, and what does it go towards? And you'll have an answer right here. As x approaches negative infinity, y approaches, and you'll have some kind of value there. Vertical asymptotes are a little bit different because we're talking about domain issues. So domain issues are what are causing those vertical asymptotes. That's what we looked at the other day when we built the table and we tried to do numbers that were really, really close to the right of our asymptote or our domain problem and to the left of that. So the notation associated with that would be as x approaches, and then what's going to go here is the number associated with domain issue. Okay? So as x approaches whatever that number is, and then we're going to say the limit as x approaches this thing, and then we're going to put equals, and sometimes we get a number, but other times we get a concept, like positive infinity or negative infinity. Okay? And then because this one right here is associated with the right, we're going to say as x approaches this number, we put a little plus sign. That means from the right. So an example of that might be up here, back in this picture. Let's imagine that this is the line x equals 3. So you could say the limit as x approaches 3 from the right. So as x approaches 3 from the right, what happens to y? It goes really, really far down. We get negative infinity. Okay. Down here, we have left. It's the same idea. The limit as x approaches, same thing as above, number associated with domain issue, here too. And in order to indicate that we're coming at it from the left, we put a negative left. And you're going to get equals, and you might have a number again, or you might have positive or negative infinity. That's not a hashtag, it's a number. Both. So this is not something that we've really touched on yet, but both means that instead of having a plus or a minus, we put neither down, and we're going to come back and spend a lot more time with this both concept. So one more color. So the limit as x approaches whatever the number associated with the domain issue, here too. And we don't put, there's nothing here. Nothing. No plus, meaning right. Plus, meaning right. And no minus, meaning left. Okay. There are some different things this one can be. This one's a little bit trickier. So this one can be a number, just like it was before. Or it could be positive infinity. It can be negative infinity. Or, this is the big one, we can say it does not exist. D-N-E is the way you see that written. Does not exist. So let's look at a couple of these. Let's look at this one right here. So we're going to use our we're going to use our fingers here to help us figure out what is going on. So let's see. This domain issue must be happening at x equals 2. We have a asymptote that's occurring. Okay. So as x approaches 2 from the right, and I'm going to take my finger, I'm going to do this. As it's coming at it from the right, what does my finger do? Does it shoot up to infinity? Yes. That means this guy goes to positive infinity. Okay. Now, as x approaches 2 from the left, what does my finger do? I put my finger on it, and I go tracing from left to right, coming towards it from the left, whoosh, starts to go down. So that's negative infinity. Okay. So here is always the question. Does the limit of both of them exist? So it only x approaches 2 only exists if, big if, these two are the same thing, meaning my fingers both go up, they both go down, or they both come in to like a specific number. So in this case, there would be like on a whole. You might have that one if it was coming towards on a whole. So if I looked up here again, you would have a limit from the left and the right being the same because they would come towards the same point. Okay. So here, this guy's going up, this guy's going down, so it does not exist. So it only exists if these two values are the same. It's called the left-hand limit. And right hand are equivalent. Okay, let's look at this one. Let's do this guy over here. So we've got, let's say that this is at 2, and this is at -2. Okay, so as x approaches -2 from the left, what does it do? Goes up. As x approaches -2 from the right, what does it do? It goes up. So that goes to positive infinity. So as x approaches -2 from the left and the right, are both the same, so you would say is +2. So that's an example of when it would be 1. In this case, we would say as x approaches 2, period, the limit, so each one of these are limits. The limit, and the limit does not exist here because they're not the same. Here they are. All right. So the limit as x approaches +2 from the right, -infinity. X approaches 2 from the left, +infinity. And as x approaches 2, are these two the same? Does not exist, not the same. So that's the first page. We'll come to the next page on the next video.